Alrighty, we are going to look at, in this video, tangent and velocity problems. And this is kind of the fundamental basics of what it means to be calculus. So we're going to take a look at this tangent line problem first, which is our limit process. So I'm going to kind of go up to the side here and just draw basic Cartesian plane. And I'm going to draw some random function here, and I'm only really concerned with what's happening in the first quadrant. I'll name this f of x, and it's a continuous function. Okay, now if I look at any two given points, so let's say this point right here and this point right here, I can connect them with a straight line, like so. And this line, by definition, is called a secant line because it crosses through my function 2 times. And if I find the slope between these 2 points, we also know this to be the average rate of change. So let me identify these in terms of their x values, their input and their output. So let's call this first point x, f of x, and we're going to move over a horizontal distance of h units, and we're going to call this value then x plus h, because I've just added on h units. And this output would then be f of x plus h. So if we find the slope of the secant line, again, that average rate of change, m is, so we've got change in output over change in input, or change in y over change in x. Hopefully you've seen those deltas before. Some of you might have also seen the slope formula looking something like this. So our slope or average rate of change would be the y sub 2, which is f of x plus h, minus the y sub 1, which was f of x, all over x sub 2, which was this x plus h value, minus the x sub 1, which was x. Because if we write them as points, or as coordinate pair, might be a little bit more helpful for some of you. So I've highlighted them as points. That might be a little bit more helpful to see. And again, it doesn't truly matter which one you're calling the first and the second as long as it's consistent. And now what you can hopefully see is that in the denominator, I have an x and a minus x. Those will add to 0. So I will say that my slope of my secant line here is f of this x plus h minus the f of x all over h. And you actually studied this as an expression in college algebra. Think about it for a minute. You might want to even pause the video. Do you remember what it's called? It was called the difference quotient. You can see that it's a difference, right? Because we're subtracting in the numerator and it's all in a quotient. So hopefully that will help you. Now you algebraically manipulated that in college algebra, maybe with or without some meaning. So let's take a look at what it means in terms of calculus and why it's this sort of tangent line problem, or why we're even going to talk about it with limits. So if that's the slope between 2 points, or average rate of change, that tells us things like if we get in our car and we drive to school and it takes us maybe 20 minutes to get there, what was our average rate of change, or what was our average speed on the way to school? So maybe you do some calculations and you determine that it was 28 miles an hour, your average speed getting you to school. Now that doesn't mean that you drove 28 miles an hour the whole time. That just means that at one point or another, maybe multiple times, you were going 28 miles an hour, sometimes greater than that and sometimes less than that. But what might be more important is talking about what's called an instantaneous rate of change. So what happens if you bring this second point up here that I'm highlighting green in along the function, and you bring it as close as possible to that first point that we talked about? A couple things are going to happen. If they are so close that they are kind of becoming one, and they only touch the function one time, then you have what's called the tangent line. Let's see if I can draw that well. Oh, looks pretty good. So the tangent line will touch or cross your function one time. So they share one common point, and around that point, it will sort of take the shape of your curve. Again, My curve was this original f of x, which I can make a little bit darker here, red, if that's easier to see. And then that tangent line just comes in and shares one common point with that function and then goes on its way. And that's called the tangent line. And what's special about that tangent line is this is going to give us what's called instantaneous rate of change. So that slope of the tangent line is going to give us that instantaneous rate of change, which is also what we will study throughout this course, our first derivative. Well, you don't really have to know the term derivative just quite yet for this topic, but the fact that we have to calculate the slope of the tangent line should be of concern, because if I just told you that there's only one point right here, how would you do that? Well, that's that second point that we were going to bring in that's almost right on top of that first point. It's so close that the distance between the two is almost zero. Not quite zero, but close to zero. So what you're going to do is you're going to bring this horizontal distance in so that your second point has an x value almost right on top of that first one. So the slope formula is the same, right? The y sub 2 minus y sub 1 all over the x sub 2 minus x sub 1. So the slope is still the same, but the only difference now is that in front of it, I'm going to say the limit as h approaches 0. Because what happens is I want the horizontal distance between the two x values to be as close to 0 as possible. So you're going to bring that second point in as close as possible to the first. So this is the slope of the tangent line, which gives me my instantaneous rate of change. And if I'm using that driving a car scenario, well, you might have averaged 28 miles an hour driving to school. But what was your speed at every given moment? So what was your instantaneous rate of change? If you look at your speedometer and it says 35 miles an hour, well, 35 miles an hour was that instantaneous rate of change at any one moment in time. And this is unique because prior to calculus, you needed 2 points to calculate slope. And now we're really going to talk about it in regards to 1 point, because that second point is going to be as close to the first as possible. So let's look at some practical examples of these. And in the notes that I provided you, you can see kind of that same language here. So before we get into the first example, it says you're going to begin with the secant line, and as the limit of delta x, or the distance between the two x values, so h approaches 0 of that secant line, then it will become that tangent line. And the slope of the tangent line is what we call the first derivative. So let's look at some examples using average rate of change, which again is probably your prerequisite skill or prior knowledge. And let's turn that into the instantaneous rate of change, which is the calculus piece. So our first question says if a ball is thrown into the air with a velocity of 40 feet per second, its height in feet t seconds later is given by y equals 40t minus 16t squared. The first question that we're going to do 5 different times is find the average velocity over the given time intervals. This is definitely what I would consider to be prior knowledge, because average velocity is really just slope between the two given points. Now, unfortunately, they give me time intervals. So this, for example, would be from t equals 1 to t equals 2. So I don't necessarily have the output, or in this case, the y or function values. I only have their inputs. So I can do these a couple different ways. So I'm going to grab my calculator, and what I will do is I will click on the y equals and type in the function that I was given. And then I'm actually going to write these as points first to see if that helps you a little bit. So what I will say is 1 comma something and 2 comma something, and I'm going to put these in the function, and I'm going to let my calculator do some of this work. I could certainly do it exactly. So I know that my table, for example, again, go to second window or table set. I think it's a little bit more efficient to have that independent variable on ask, so you can type in whatever you want. Then when you go back to table, you're going to type in 1 for your input and then 2 for your input. And since these are exact, you certainly will want to keep everything exact the whole way through. So this is 1 comma 24 2, 16. The other thing, of course, that you could do is you could look at the graph of this function, and I've changed the window accordingly. So if you want to have it match mine, you can certainly look at the x-min, x-max, and the y-min, y-max. I very much like to see my axes. I don't like my graph to just be in the middle of the sky somewhere. So I can see the vertex, right? I can see the behavior of the graph, and I know this is a parabola that opens down, so I'm seeing the entire picture here. And I know what the behavior does, once it leaves my window. So I could also have said secant calculate or secant trace a value when x is 1. And then the nice thing is that it does put my cursor there, so I can kind of keep an eye out for that. And then secant calculate a value at x equals 2, or an input of 2, and I could see that if 1 was up here and 2 is right there, and I connected these 2 points, that's going to be finding the average rate of change between those 2 points. So I definitely expect that to be a negative slope. And so what I would say is m equals the y sub 2 minus the y sub 1 over the x sub 2 minus the x sub 1. So m is negative 8, and I definitely am going to go through and put a label on all of these once I am done. So you could certainly do that for all of these. You could list what this point is when x is 1, which I kind of already know. It's 1, 24. And then what is it when your input is 1.5? Again, making sure that you're keeping all of these exact. So I could do that one more time, and I could use my graph, or I could use my table. Just again, making sure that that output is in exact form, and it's 24. And so if I calculate the slope myself, I can see that when I subtract those numerators, I'm going to get 0. Okay, so now a different way that you can look at this is you could just use your home screen, and I could tell my calculator, like let's say I didn't necessarily need those output values or need to write them down anywhere. Well, I could say that my slope is the function's value at 1.1 minus the function's value at 1 all over that 1.1 minus 1, right? That's me finding the slope. And again, you're going to want to keep everything exact throughout this course as much as possible. I can use my vars, which is kitty corner next to my arrows here. So vars. Go over to y-vars, these are your y variables, hit enter on function, that's the mode we're in, and I typed in my function into y1, so I will hit enter, and then I'm going to say at 1.1, and I will subtract vars, go over to y-vars, function y1 at 1, don't forget the at part, so that is 0.64 over 0.1, and hopefully you know how to divide with the decimals. The slope then would be 6.4. So one other way that you can use your calculator, I'm going to do the same thing but get there a little bit differently. Okay, so I have my slope set up here. So in your, I guess the new software, it's not really new anymore, but you have a whole additional set of features. So if I hit alpha and then the calculate, so alpha is the green, and then the trace or calculate, I see y1, so that it goes right to the y variables here, or y vars. So y1, and I can hit enter at 1.01 minus, I'll do it again, alpha trace, hit enter on y1, or wherever you put your function. Or you know y1 is 24, so maybe you just use that. That's fine too. So I get 0.0784 over 1/100th, and so my slope here would be 7.84. Okay, one last one. Go ahead and try and do it yourself, and then let's check our answer. Okay, now if you used your table for this one, just humor me real quick here. I'm going to put in 1.001. And see, what I want you to make sure you understand is that your table width that they're showing you is only so wide. So even if your number continues on and has 5, 6, 7 decimals in the value, it's only going to show you so many because it only has room for so many. So if you physically hover over and put your cursor over that value, down below the table, it will try and show you as much of it as it can. And so that's where I'm getting the 0.007984 from. Okay, so now it's important that we label these. So let's take a minute and look at these labels. Hopefully you've checked your slope and hopefully you got 7.984. Okay, and I have them all on one screen now so I can label these. What was important to note was that our original had height in feet and the time in seconds. So as you're finding average velocity or slope, keep in mind that this was delta y over delta x, or change in output, which was height in feet, over change in input, which our input were seconds. Also, we're talking about an average velocity, and it told you a velocity in the problem to start with, so hopefully those units or labels will match. So all of these deserve feet per second. Okay, now the question might become, does it make sense to have -8 feet per second? Sure, that means that you're moving at 8 feet per second backwards or in an opposite direction because velocity has direction attached to it, which we'll talk about throughout the course. Does m equals 0 make sense? Absolutely. 6.4 feet per second, then 7.84 feet per second, and then 7.984. Now let's take a look at what these intervals are doing. So first you were going from 1 to 2, then from 1 to 1.5, 1 to 1.1, 1 to 1.01, and 1 to 1.001. This is purely for visual or setting you up for something. They might not always be as obvious as this, but let's look at the graph of what this means. So what this is saying is that if this is at t equals 1, right where my cursor is on that graph, you are first going from 1 to 2. So that's going from t equals 1, right about here, to t equals 2. Okay, and then from 1 to 1.5, and then from 1 to 1.1, so you're getting closer and closer and closer to this just one singular value of t equals 1. So they're becoming so close that they're almost becoming 1 point because the horizontal distance between them is getting closer and closer to 0. So I left some space if you'd like to write any notes for yourself on how to use the calculator and which method you might find to be most efficient. Notice that through each method, no matter how I calculated those values, I have exact numbers. So now the question becomes the calculus question: estimate the instantaneous velocity when t equals 1. So if I take a look at these slopes, it appears, if I look at the last few here, it's going 7.84. Those are pretty close together. These are even closer together, and my slope is 7.984. So these are the closest two that I have. So if I'm estimating the instantaneous velocity when t equals 1, I'm going to use the points that I have that are closest together surrounding 1, which is the very final interval. And so I would say my slope is approximately 8 feet per second. You could also argue 7.984 feet per second, but we're rounding. We're just using this to estimate, so 8 would be fine. All right, let's take a look at some other examples. Again, this question too might be something that you did in a pre-calculus course or a college algebra course. If you're looking at this function and you want to find the average rate of change, this is your interval that's given. So I'm going to identify the 2 points. So here's -1, 2 would be 1 coordinate pair, and then 2, it looks like -4. So I could certainly do this just using the slope if I'm algebraic in thought. So y sub 2 minus my y sub 1 all over my x sub 2 minus my x sub 1. Watch your parentheses there. So I do have -6 over 3. So my slope should be -2. There were no units or anything to label here. The other way that we learned was literally, if we're counting slope, we could always just count rise over run from one point to the next. So let me just remind you that it doesn't matter which point you start with. So let's say we start with this green point up here. Well, to get to this other point, I'm going to rise -1, -2, -3, -4, -5. I'm going to go down 6. So that's a rise of -6. And that puts me here. X marks the spot. And then to get to that red point, I need to run 1 to the right, 2 to the right, 3 to the right. And moving to the right is positive. And so I still see that slope of -2. Now, if I started with this point that I'll make black, so I'm going to start with the point that's in quadrant 4. I would rise up 1, 2, 3, 4, 5, 6. So my slope would be +6 because my rise was up 6. But then I have to go to the left 3, which would be a -3. And again, we know our rules for multiplying and dividing are that if I have a positive divided by a negative, ultimately it just ends up being negative. So it really doesn't matter which way you look at it in these situations, you end up with a slope of -2. So hopefully that one was a little bit of a review for you. And again, that's average rate of change, just saying from start to finish, your average rate of change or slope was -2. Okay, last question for this. What if we were given information in table form or data that we had to then analyze? So this table shows the amount of full-time students that PVCC had each fall semester during the years 2014 to 2019. So what you can see is the way this data is given, I don't know if you've noticed, but the students are on the top and the years are on the bottom. Well, most of the time you're going to notice that time is your input, right? Because time is something that is going to increase, right? Minutes, seconds, hours are going by. That's sort of that constant. And then our students are going to depend on what year it was. So our independent variable is our year, so that's our input. And our output, or our dependent variable, is our number of students. So every time I'm asked to label my answer, I need to think of any type of rate of change, whether it's average rate of change or instantaneous rate of change, as output over input. All right, so this label is going to be students per year. Okay, so let's calculate these. Well, it says determine the average rate of change from 2015 to 2017. So I'm only looking at this information right here and this information right here. Okay, for this question, nothing else matters. Again, 2015 and 2017 are my years. Those are my independent variables. So those are my inputs. So what I want to do to calculate this slope or average rate of change is say that this is going to be the output. So I'll let this 2017 be my second point. So it'd be 8,447 minus 8,684 over 2017 minus 2015, which I know to be a 2-year difference. But if I use my calculator to do that subtraction, which is fine, I do get negative. I get negative 237 over 2, or my slope being negative 118.5. Now, before you get too carried away and just move on to the next question, let's think about whether or not this makes sense. What does this really say? Well, again, this is a slope or an average rate of change across these years. So what this is saying is that you have decreased by approximately 118.5 students per year. So you can use the word decreased, or in other words, that slope being negative, right, means that your enrollment, if you will, has gone down, right? Because this is enrollment. Well, sure it has, because you started in 2015 with over 8,600 2 years later, you only had 8,400. So we've lost students. So it should make sense that that slope is negative. So if I'm just answering the question, find the average rate of change, it'd be approximately negative 118.5 students per year. That is not suggesting that you can have half of a student. That is a rate of change. So estimate the instantaneous rate of change, however, in 2018. Well, I can only use the data that's given. And let me repeat that because it's a very key idea. You may only use the data that's given. So if I want to find the instantaneous rate of change surrounding 2018, I want to use the closest points or the interval that is closest to 2018 that I can. Well, the only data that I have to work with then is 2017 and 2019. So what I'm going to do is find the slope from 2017 to 2018, and I'm going to find the slope from 2018 to 2019. So go ahead and pause this video, do that now, and let's compare our slopes. All right, go ahead and unpause that video. Hopefully you have calculated the average rate of change between 2017 and 2018 to be about negative 332 students per year. And between 2018 and 2019, you should have found that that slope or average rate of change was negative 215 students per year. Again, I did label both of those so you could see. So that doesn't really answer our question yet, though. We're going to find the instantaneous rate of change in 2018. Well, this is before 2018, right? From 2017 to 2018. And then this is after 2018. So if we just simply average these together, it's got to be somewhere in between negative 332 and negative 215. So for now, just to get a good estimate, we'll go ahead and average these two. So we will add them together and divide by 2. So I will say that my instantaneous rate of change, or IROC, is negative 332 plus this negative 215 all over 2. And this is going to turn out to be approximately, I mean, this is exact, but negative 273.5 students per year in 2018. So this was a decrease in 2018, in that one moment in time, of approximately 273.5 students per year. Again, it has to be somewhere in between that negative 215 and that negative 332. So you'll capture more of these instantaneous rates of change as you work with the derivative more and more, and as you learn more about limits as you continue through your calculus course. I hope you found this video helpful. Thanks so much for watching.